Alright, we're going to continue with section 14.2 in this video, and I'm going to work exercise 11 on page 921. So number 11 says, or the directions say in exercises 7 through 13, find the volume V of the region by using iterated integrals and polar coordinates. And they say the solid region inside the sphere x squared plus y squared plus z squared equals 4, outside the cylinder x squared plus y squared equals 1, and above the xy plane. All right, so I'm going to kind of go a tad bit astray from our process, and I'm going to actually sketch this in 3 dimensions first, which we rarely will ever do, and you won't have to do in general, because I'm going to show you how to get through this problem without sketching in 3 dimensions as well. But I am going to just show you what it is, though. It's good for you to be able to visualize these things in 3 dimensions because eventually we will get to triple integrals. But right now we're doing double integrals, and our regions will be 3-dimensional regions, but you won't have to. I still will show you how to get through those by sketching 2-dimensional region as much as possible, but sometimes you will need to be able to visualize the things in 3 dimensions. So this is a kind of a good precursor to that. So it tells us that our the solid region inside the sphere and outside the cylinder. So it doesn't specify a quote unquote top, and they say and above the XY plane. So they give us our bottom. Now, so we're above the XY plane. So what we'll do is we'll sketch a hemisphere. Above the XY plane. So we have something like that. And then it said we are inside of here and outside the cylinder. Now this hemisphere has radius 2. So that's 2 right there. And then the cylinder has radius 1. So the cylinder so we have this cylinder inside of the sphere. And now the region that we're considering, that we're trying to find the volume of, is this region that is, remember, we are inside the sphere and we are outside the cylinder. So now if we had an entire sphere here, the way I tend to describe this is you take an orange and you poke a straw into that orange, then you're looking at the volume. Now we're just looking at the top half of the orange in this scenario. You're looking at the volume of the orange that is outside of the straw. And for us, it would just be the top half of that. So the part of the orange that's inside the straw, we could like kind of blow that part out, and we're not considering that part at all. So we're not considering whatever's inside of here, just that outside part. Now, the reason I drew this in 3 dimensions is because now it makes it a little bit easier for if you were looking at this from above to tell what the region would look like. The region over which we're integrating, which is that little part down there that has the dotted lines around it, we're going to integrate over that region. So you can see it's like it's an annulus or a ring, but we're still going to go through if we didn't have this and look at our approach that we usually use. So let's sketch the region here, the region R here. So what the region R is going to look like, and remember I said I still will go through this as though we did not have the 3-dimensional sketch. So we're going to have a circle of radius 1, and a circle of radius 2. We have these 2 circles. And we're looking at this from above. So our shaded region, the region over which we're integrating, will be that right there. Or actually, we look at it from above, or we're really are just smashing it down into the XY plane entirely, because I don't want to look at this thing from above. I just want to look at the part in the XY plane. So that's probably a better way to describe it, is we're looking at just the part in the XY plane. And now it's easy to tell what our radius varies between, and what our radius varies between 1 and 2. Our theta goes from 0 all the way around to 2 pi. But let's look at this as though we didn't know what that looked like. So we kind of were given our sides and we were given our bottom. So our bottom we knew was z equals 0. Our top, they didn't specify what the top was, but they just said inside of the sphere and outside of the cylinder. So we'll just look at our sides, and that will give us our quote unquote top. Now, one thing to keep in mind here is this is one of those scenarios where we were not given an integrand. So we're going to have to set up the integrand ourselves, whereas in the previous set of problems 1 through 6, they give you the integral that they want you to evaluate. So now our sides, and remember in a problem like this, usually our integrand is top minus bottom. So let's look at our sides and get this set up, and then we'll figure out what our top is, because we still are kind of missing that information. So our side is going to be the region, because they said inside and outside. So that's how I'm getting this. So region between the intersections of z equals 0 with the top, whatever that is, and z equals 0 with x squared plus y squared equals 1. All right, so now from the fact that we're inside of the sphere and outside of the cylinder, and we're looking at the z equals 0 intersected with that, that gives us that's kind of our bottom, because when we intersect z equals 0 with the cylinder, we end up just getting this little small circle right here. So our top is going to be from the sphere or the hemisphere. So that's going to give us z equals, what was this radius, 2. So this is z equals, now they gave us the entire sphere, x squared plus y squared plus z squared equals 4. But we would solve that for z, because we're only looking at the top half of that, and we would have the square root of 4 minus x squared minus y squared. So we already can quickly see what the intersection of z equals 0, what that is. It is just that circle. Now we need to look at the intersection of z equals 0 with this right here, and that will give us what that outside circle is. Now, of course, with this 3-dimensional sketch, you all can easily figure out what that is, but I just wanted to go through it that way as well. So now let's do it over here. 0 equals the square root of 4 minus x squared minus y squared. Then square both sides of that, and we get x squared plus y squared equals 4. So now we want to do this in polar coordinates. We don't want to do this in rectangular coordinates, like, because we look at this region and we try to figure out if it's type 1 or type 2, and we end up in a world of trouble. So instead, polar coordinates are much easier. So now we have everything set up here. Notice your ability to visualize things in 3 dimensions will help you and make things probably a lot faster than trying to go through this process. So it is useful to at least make an attempt now. It's not vital at this stage that you're able to do this, but it will be vital a little bit later in the course. But we'll just build up to that though. All right, so now our region R. Remember, we want to do this in polar coordinates. So let's just label some things by our picture up here. So that's 2, That's 1 inside of there. So our R varies from 1 to 2, and our theta, because we're going around the full circle, varies from 0 to 2 pi. And I want to write that up there so make sure we don't accidentally try to do this in rectangular coordinates, which will make our life much more difficult. So now here we have R is equal to set of points R comma theta, where R varies between 1 and 2, and theta varies between 0 and 2 pi. All right, now we are ready to actually set up our integral and evaluate it. So our integral, the double integral over R. Now what is our integrand going to be here? It's still going to be top minus bottom. So the top minus bottom dA, which for us is the iterated integral from 0 to 2 pi, and then from 1 to 2. Our top was z equals the square root of 4 minus x squared minus y squared. So we don't include the z. It would just be this minus our bottom, which is 0. So this minus 0, but make sure you put things in polar coordinates. So we don't want any x's and y's swimming around here. So it's just going to be the square root of 4. Then what is negative x squared minus y squared? That's just negative r squared. So 4 minus r squared. Then don't forget about your r, which is just part of when you integrate in polar coordinates, and dr, d theta. All right, so that's the setup for that integral. And this one was a fairly straightforward integral if you let u be equal to, so let u be equal to 4 minus r squared, and then du would be equal to negative 2r dr, and we see that r dr right there, and you can finish this off using u substitution. So I'll let you all finish that off, finish off that integral, and I'll stop this video here, and then we'll do another some more exercises from section 14.2 in the next video.